So today is the first installment of this series of infrared synergies within the infrared archive, which maybe we should have named everything you can do by combining data from the Earth archive together. And well, our first talk is from Wafa Zakri, and she's going to talk about protostars, but I wanted to mention that there will be 5 different talks. And this series was made in support of the SOFIA archive research proposal call, which is ongoing now and which encourages using data in the archive and proposes funding for US-based proposers. So I'll put a link on the chat if you need to know more about this call, and I hope some of you can take advantage of it. Wafa Zakri, you got your PhD a couple of years ago from University of Toledo with Tom, who is also online and kindly sharing the screen. And since then, you've been an assistant professor at the physics department at Jazan University, so Saudi Arabia. And you're also assistant chair in the industrial engineering department. I think this year you published this very cool paper on protostars in Orion and outbursts using really a large number of facilities data analyzed together. So I thought this was be a great example of infrared synergies. Wafa, you can start whenever you want.
Okay. Hello, everyone. It's my pleasure to being with you giving this talk that is focusing on the search of outbursts from class 0 protostars in Orion molecular clouds and how we determine their rates, amplitude, and duration using datasets from Spitzer, WISE, SOFIA, and Herschel. Next. Next. So first, let's introduce the protostar components. As we see in the image, the basic components are the infalling envelopes, the accretion disk, and the central protostar and bipolar outflows. Next. So here, I don't know if we can open the video, but here we present the evolution of, I'm sorry, can you go to the previous one?
The video does not work. I could not get it to work.
No. The slide before that is the protostellar evolution. The protostellar evolution. Yes. Yes. Here we present the evolution of protostellar SEDs, class 0. Tom? The protostellar, here we present the evolution of protostellar SEDs, the class 0 protostar, a class 1 protostar, a flat spectrum protostar, and class 2 pre-main sequence stars with disk respectively. These SEDs show the evolution of stars formation from a deeply embedded protostars class 0 to pre-main sequence stars with disks. The SEDs of each protostellar phase shows the peak wavelength of each class. So we can see in the left SED that the class 0 protostars peaks at about 100 micron. So they deeply embedded sources within their envelopes and usually require measurements in mid to far infrared space, infrared from the space to or sub-orbital platforms. Next.
Do you want the outburst one? Sorry, I think we had a mismatch in our presentations. Is this the one?
Yes. So because we're not able to open the video, but I'm trying to explain the video. The video show that the source is the spiral arms and the disk moving around the central star, and the bottom is showing the records of the mass accretion during that. So there is different peaks going up and down. So this is the general idea of the videos, and to explain that, the model is from Verbiov and Paso 2010, is presenting the simulation of protostellar disk fed by the infalling envelopes. So this shows the gravitational instabilities in the disk can derive rapid change in the accretion. So the disk, when it's moved around, it's showing the continuously accreting gas from the envelope, and the mass of the disk then growing until becomes gravitationally unstable. And this happened when the rate of the infalling material becomes, when the infalling materials onto the disk is faster than the rate of infalling from the disk into the protostar. So so when this happened, as I said, when this happened, the disk can become gravitationally unstable, and its own massive gravity causes the fragmentations. And it's from spiral arms, when it's moving, the spiral arms, the gas rapidly dumped into the central stars, creating luminous outbursts. So the records at the bottom that I'm trying to explain, showing what it's showing the accretion rate of driven spiral arms versus time, as you see at the bottom. So this showing the accretion rate of the driven spiral arms versus time, as I said, and showing the high burst of accretion down to the central star. And we see that the luminosity of the star is dominated by the accretion luminosity, and thus the change in the luminosity are due to the change in the accretion. So next, yes. Here is the light curve example of the burst protostar detected by Spitzer. This burst protostars called NGM 1472, named by Megath et al. 2012, and the light curve shows the magnitude change versus MJD, the modified Julian date for Spitzer launch date. As we see here, the light curve shows the rapid increase in the mass accretion between 2004 and 2009, and continued to 2016, and then it may begin to fade until 2019, and we don't know after that. So next, yes. Here are the data sets we use for our study. The study combines the data from Spitzer, WISE, SOFIA, and Herschel to identify and determine, as I said, the rate, amplitude, and duration of the outbursts from class 0 protostars. So from Spitzer observations, we use data that were observed by IRAC, observed by IRAC 1 and 2 at 3.6 and 4.5 micron between 2004 and 2019. So first set from Spitzer is the Orion survey GTO observation that were made in two epochs separated by 6 months in 2004. And we also use the extension single epoch field that were made in 2007 and 2009. Then we also use the WISE over warm data at 2009 and 2010, this including 80 fast cadence observation in 2009 and in 2009, and in 2010 it's including 11 observations. So we are also using Spitzer Warm Mission Observation Orion TFE, the final epoch of observation. This covered the entire 2004 Spitzer Orion fields in 2017. The last set we use from Spitzer is the Spitzer Beyond observation that were made in 2019, where all of the unknown or all of the known YSOs within 1 magnitude variation between 2004 and 2016 and 17 were again observed by the same wavelength observation in 2019. Here all the data sets we use from Spitzer to detect the outburst. Then we use WISE and NEOWISE to monitor the sources for extra time. So we use WISE and NEOWISE. From WISE, we used all sky data at 3.4 and 4.6 micron that observed entire Orion in 2010. We also used data from 3-band cryo that were observed 6 months later than the all sky that at the same wavelengths of observations. The last set we used from WISE is NEOWISE, Near Earth Object WISE, that were made between 2015 and 2020. Then we used SOFIA forecast photometry that were observed in 2019 at 19.7 micron, 25.3 micron, 31.5 micron, and 37.1 micron. The last sets we use for the study are the far infrared data from Herschel, Spitzer, and SOFIA, where where from Herschel we used data observed by PAC 70 micron and 100 micron in 2010. From Herschel we used data. From Spitzer we used data from MIPS 24 micron in 2004 and 70 micron data in 2010. And finally, from SOFIA, we used HAWC 89 micron data in 2019. So, next. Here our targeted sources. In Orion A and B. The background maps are from Stutz and Gold 2016, and the data points are Spitzer Spitzer Dusty YSOs from Megath et al. 2012-2016. So the YSO of our protostars are in Orion A and are demonstrated by red points, and the disk sources are in aqua color. The rest are the targeted. The rest sources are targeted outside the YSO of our field in both Orion A and B. So the orange points are the protostars, and the pale green are the disk objects. Next. So here, from the comparison of Spitzer Cold and Warm Mission 2004 and 2017 for 319 protostar in 3.6 and 4.5 micron Spitzer band, here is the first detection of outbursting class 0 protostar HAWC 383. So HAWC 383 first announced as outbursting class 0 protostars by Saffron et al. 2015, detected by Spitzer at 24 micron. So right is the HAWC 383 MIPS 24 micron images, pre-burst in 2004 at the top and post-outburst in 2008 at the bottom. Left is the spectral energy distribution of the source, flux versus wavelength at 24. So here at 24 micron, the pre-burst and the post-outburst are within an arrow, and demonstrating the increase in the luminosity by a factor of 35 between 2004 and 2008. Next. Here we present the light curve of HAWC 383 at 4.5 micron. The times of the MIPS, FORCAST, BACS, and HAWC observations are shown by the vertical lines. So the light curve shows Spitzer observations made in 2004, the WISE over observations made in 2009 and 2010, the Orion TFE in 2017, and finally Spitzer beyond observation in 2019. And the light curves here shows the entire burst event, which had a duration of about 15 years. Next. The second two outburst detections from the comparison of Spitzer 2004 and 2017 are the previously two unknowns class 0 protostars HAWC 12 and HAWC 124 that were announced by Zakri et al. 2022. So the images we see here are taken by Spitzer IRAC 2, and that detected the detected bursts are marked in green. Upper images are HAWC 12 pre-outburst in the epoch of 2004 at the left, and post-outburst at the right of the burst discovered by the Orion TFE 2017. Bottom are the pre to post outburst of HAWC 124 at the same epochs of observations and also the same wavelengths. And as we see, both protostars have nearby YSOs that may be a companion. So HAWC 12 is the east and its companion is at the west side. It's separated by about 6 micron, it's separated by about 6 arc seconds from a YSOs later resolved into a closed binary by Taupin et al. 2020. Bottom images are presenting HAWC 124 with its companion, a flat spectrum protostar HAWC 125. The physical separation between them is about 9 arc seconds, and it also shows an extended scattered light nebula. Next. Here we see 4.5 micron curves of HAWC 12 top and HAWC 124 at the bottom. The left panels show the cryo observations from 2004, WISE over data from 2009 and 2010, Orion TFE measurements from 2016, 2017, and the Spitzer beyond observation in 2019 for both sources, HAWC 12 on top and HAWC 124 on the right, on the left bottom. So left upper light curve shows that HAWC 12 rose rapidly between 2004 and 2009, sustained its brightness through 2017, and faded by about half magnitude by 2019. Left bottom light curve shows that between 2004 and 2017, HAWC 124 brightened by about 2.3 magnitude at 4.5 micron and didn't fall within WISE over detection and was not observed between 2004 and 2017 by Spitzer. Then it shows about half magnitude also fading between 2017 and 2019. So because of that, we are supplementing our work using NEOWISE data. So right sets showing the light curves from Spitzer 4.5 micron, WISE and NEOWISE 4.6 micron light curves of HAWC 12 on top and HAWC 124 at the bottom. But because our class 0 protostars here have a nearby companion and WISE has lower resolution than Spitzer, so the source with its companion blending together. And so to do the comparison, we degraded the resolution of Spitzer images to be the same as WISE images. So the Spitzer detection here for both sources is demonstrated by black points, and WISE and NEOWISE by red and orange points. So the photometry of Spitzer is given related to the Spitzer TFE data points and relative to the average of the three NEOWISE data. The closest one together is about in 2018 for both HAWC 12 and HAWC 124. So these data also, the combined data or the degraded data also consistent with the HAWC 12 burst occurring between 2009 and between 2004 and 2009 that detected by Spitzer itself. And as we previously demonstrated that by Spitzer alone, and HAWC 12 NEOWISE data here show that by 2015, the source started fluctuating during its burst with peaks at brightness separated by the interval of approximately 2 years of fluctuations. But for HAWC 124, the data shows that the source is rising in 2010 during the WISE observations and is approximately midway between 2004 and 2015 to 2019 max. This suggests that HAWC 124 may have occurred in its burst may occurred in 2010, or it could be more gradual rising between 2004 to 2016-17, and the protostar peaks in 2015 and similar to the HAWC 124 fluctuating during the burst. And at the end, we see that both bursts last for about 9 years and both may declining by 2019. Next. Here are the last two burst detections from the more evolved protostars. Flat spectrum protostar HAWC 223 and class 1 protostar HAWC 41. So HAWC 223 at the left, showing 3.6 micron in red and 4.5 micron in black detections. So as we see here, HAWC 223 didn't fall within WISE of our detections or within WISE of our field, and it shows about 2 magnitude outbursts between 2004 and 2017 or 2019. And HAWC 41 also show about 2 magnitude bursts between 2004 and 2008, and then it may become down. Next. Here, to measure the rate of the burst from the 3 detections over 13 years, we estimate the rate of the burst for the class 0 protostars. So for 3 bursts, NB equal 3 out of 92 class 0 protostar in Orion, this NP within a time interval of 13 years, this delta T. So the burst rate for class 0 protostars is estimated to be about 2.25 times 10 to minus 3 per year. So this is corresponding to the burst interval equal to the 1 over rate, and this gave 1 burst every about 400 years for each protostar. Next. Here we present the probability density function top panels and cumulative probability distribution at the bottom for the burst intervals. So we calculated the burst interval for the 3 pairs of samples. Left is 92 class 0 protostars appear in blue curve, and 227 class 1 and flat spectrum protostar orange curve for the entire field or for the entire Orion macular clouds. Middle is the WISE over field of the ONC, which this 27 class 0 protostar and 45 class 1 and flat spectrum protostars, and right is all the 319 protostar in the entire Orion and 72 protostars in the ONC region. So the reason of studying the burst amplitude at the middle for only in ONC region, that because HAWC 383 outburst subsided by the time of the Orion TFE survey. However, it was only detected when it fell within WISE over observations. Thus, protostars outside the ONC that burst after 2004 and declined before 2016 would be missed here. So because of that, this pair has more complete, the middle pair has more complete time coverage, but contain a smaller sample of protostar than the first pair. So, assuming a burst interval is 13 years, and from the number of bursts and number of protostars, and the probability distribution can be driven from the following following the approach from Fisher et al. 2019, where they presented a model for a number of outbursts, where the probability of the number of outbursts in our sample given as NB, and this given by the posterior probability distribution. So for the burst over the time interval delta t with the rate equal to 1 over IB, the chance of detecting one burst or more from a given data is given by 1 minus e to the minus delta t over IB. So from that, we found that class 0 protostars have a median burst interval of 438 years. So and also this is a factor of 4 shorter than for the more evolved class 1 and flat spectrum protostars that gives 1,741 years median burst interval. And at the middle, we found that the interval for class 0 protostar shrinks to the 199 years for the ONC sample, and still a factor of 4, also shorter than more evolved protostars in ONC regions, and this gives about 823 years. The last one, by the same approach, we got the median burst interval for all protostar in the entire Orion and compare it to the all protostar in ONC, and we got that for the all protostar is 879, and for all protostar in ONC 341 years. So down panels are the cumulative probability distribution for the burst interval. So within 95 confidence interval using logarithmic prior, and we from that we found the burst interval for all protostars is consistent with estimate of 1,000 years. So I think Tom can continue the discussion or the talk.
Okay, thank you, Wafa. So maybe we can take questions at the end. So Wafa has basically described how we calculate the interval between bursts, given the small number of outbursts that we find from the class 0 phase. And so now we have these burst rates, although as you can see, there's large uncertainties in the actual burst interval basically because we have the statistics are sort of poor with only 3 bursts. But they're getting better with time. Now, what we really want to understand is how much material is accreted during the outbursts, right? As Wafa described earlier, the interest in outbursts is partially driven by the desire to know whether if the protostars accrete objects, or protostars accrete mass in sort of a steady fashion, or whether protostars accrete mass primarily during these outbursts. And so we can actually calculate using this formula from Fisher et al. 2019, the ratio of the mass accreted in burst to the total mass from this equation here, which looks a lot more complicated than it is. But there's 3 factors that we need to know to determine this ratio. One is the amplitude of the burst. How much did the mass accretion rate rise? And of course, that's really how much did the luminosity rise, because the luminosity is proportional to the mass accretion rate. The next one is the interval between the bursts, which Wafa had just mentioned was found to be roughly 400 years, although with some uncertainties. And then there's the duration of the burst, which all of our bursts appear to be going longer than 9 years, and could go as long as 15 years in the case of HOPS 383. And if we know all of these factors, then we can at least make an estimate of whether most of the mass is accreted during burst or whether a small fraction is accreted during burst using this equation. All right, so the place where SOFIA and other instruments come into play, sort of the multi-wavelength aspect, is primarily in the determination of A. Right? And part of the reason is that the light curves, the best light curves we have, and as you can tell, they are very sparsely sampled at 4.5 microns, but still those are the best light curves we have. And just to give a sense of the importance of those, for class 0 protostars, we really can't monitor them at wavelengths of 2 microns or shorter. So you really need sort of mid-infrared data to determine, when there's a burst. But the 4.5 micron flux from the protostars primarily comes from scattered light from the inner disk. And it's not really a good measure of the change in the luminosity of the protostar. This is a plot of models from Furlan et al. 2016, where she has a grid of protostellar models, and the only thing that's changing here is the luminosity. And you can see there's actually a fairly nice, although a very nice continuous change in the amplitude of the SED as you go up in luminosity, particularly in the mid to far infrared when you go out from 20 microns to maybe 100 microns. There's a little bit of the shift forward to shorter wavelengths of the peak, but overall, if you want to measure the change in luminosity, it's best done in this longer wavelength regime from 24 to 100 microns. And that's exactly where MIPS on Spitzer, Herschel PACS, and then also SOFIA with FORCAST and HAWC observe. So for example, with HOPS 12, we actually measured the amplitude of that outburst by comparing MIPS data to PACS 70 micron data. And there's a description of this in Zakri et al. 2022. As you can see from the 4.5 micron image, it's actually a double source. And it's the source on the west, the source to the right that's outbursting. And so we had to do some sort of finagling to subtract out the component from the companion to the east and compensate for that in the MIPS 70 micron data. So it's tricky if comparing to PACS to MIPS 70 micron data, particularly since there's a lot of calibration issues with the MIPS 70 micron data, saturation issues, and very low angular resolution. Comparison between PACS 70 micron and HAWC Plus, on the other hand, is actually quite effective because the angular resolution is a little bit worse with HAWC Plus, but the data is actually very similar. And in the case of HOPS 383, it turns out PACS measured the outburst near the peak, and then HAWC Plus basically measured it after the outburst. And so we managed to determine the amplitude of that outburst by comparing these 2 observations, the right one taken by Will Fisher. Right. And in fact, here is just a comparison. Will just sent me these. He has a whole number of protostars that he's observed with HAWC Plus. And what you see here are in the circles, the PACS data from Herschel. and then the HAWC plus data into red squares. And you can see that HOPS 383, as we saw at shorter wavelengths, basically has declined dramatically by a factor of 10 almost. Its outburst appears to be over. While HOPS 124, although it looked declining in 2019 in the NEOWISE data, seems to have gone up a little bit by 2021. So that outburst is probably not over, and we're still digesting that data. We can also use forecast. Here's an example of HOPS 124, which wasn't observed by HAWC or MIPS 124, unfortunately. And so here you can sort of see the differences of the 24 micron image, where you see HOPS 124 to the top and HOPS 125 to the bottom, which is a lower luminosity source. And by the forecast epoch in 2019, it's undergoing outburst. I wrote post outburst there, but that was actually a typo. It's during the outburst on the right side, so excuse that. Now, if you're making comparisons with forecast, I'm just going to dive a little bit with the remaining time into some of the difficulties here. Just remember the band passes for MIPS and forecast are not very well matched. For example, in the orange line here, if you can pull that out with your eyes, that's the 24 micron MIPS band pass, which extends actually quite a long ways from 20 to 30 microns. And then in the green, you see the forecast 19.7, you see the 25.1 micron, and then at longer wavelengths, the 31.7 micron band passes. And overlaid, you can see the IRS spectrum of HOPS 124. And so you can imagine that what the different band passes measure can really strongly depend on their wavelengths. And it's not, here's another example. This is the SED of HOPS 383 plotted. It's actually a model SED in this case, plotted over those sources. So if you're comparing amplitudes measured between forecast and MIPS, my point is that you actually have to do this comparison fairly carefully. And if you read the appendix in Zakri et al. 2022, we actually go through that. So I'm going to skip a little bit over this, but just to remember that when you measure things, over a filter, you're not really measuring a flux density. You're measuring sort of an integrated flux, and you have to make color corrections when from going for between, say, the 24 micron filter of MIPS and a 25.3 micron filter from forecast. Just don't assume that they're the same because the central band passes are the same. So when we do this, we can actually determine the amplitudes of the outburst. And unfortunately, because we still have a large uncertainty in the interval of burst, we still have large uncertainties in the fraction of mass that's accreted. For example, here we have 3 different test cases where we have the interval of burst is 438, or as small as 200, or as long as 1884 years to sort of give you the full confidence interval. And the amount of mass accreted goes from anywhere to 3 to 23%. And if you make a further correction by saying, okay, in addition to the accretion luminosity, there's an intrinsic luminosity to the source that I need to correct for. The accretion during outburst could be 39%. So if it outbursts every 438 years, those outbursts last 15 years, the amplitude is 3.7, 40% of your mass is being accreted during the outburst. A similar analysis for HOPS 124. Here again, if we choose we have a range that goes from 4 to 16%. The 4% is if the interval for burst is at the low end of our confidence interval, about 2,000 years. And then if we actually correct again and assume that it has an intrinsic luminosity of 1 solar luminosity, and then the accretion luminosity is added upon top that, it's basically 33%. So it's significant, but it's not the dominant form. Right? HOPS 383, that burst was more significant. It was a factor of 10. And if you do the full analysis and assume that there was maybe a solar luminosity or something of intrinsic luminosity, it could be that for that particular source, 100% of the gas, at least during the class 0 phase, may be being accreted during the burst. So we don't have a very definitive answer here, but we do sort of find that there could be a significant and in some case dominant mass accretion during the burst. On the other hand, we should not go and assume that all the mass is accreted during burst. There's a good case to be made that it might be more on the level of 30% is accreted during burst and not 100%. And of course, as we get more data, and refine the interval of outbursts by detecting more outbursts, then we will, refine this number dramatically, right? And so just a quick summary, we basically found 3 outbursts out of 92 class 0 protostars, and that gives us a range of maybe 400 years. It could be as small as 200 years if we just use the data within the YSOVAR range, as Wafa explained. And this appears to be a factor of about a rate of that's factor of 4 higher than more evolved protostars. These outbursts seem to last at least 9 years, maybe as much as 15 years. And we can use the data from SOFIA, Spitzer, and Herschel at longer wavelengths to estimate sort of the amplitudes of the bursts. And then by combining these burst intervals, the durations, and the amplitudes, we can actually estimate the fraction of mass that's being accreted during the burst phases. And these may be as low as 3% or as high as 100%, right? So we think it's significant, but we really need to also, with time, as we detect more bursts, refine some of the statistics. Finally, I just wanted to mention very quickly that there's some new work that Sam Federman is about to submit, where we're using ALMA data to better refine the evolution of protostars by comparing sort of the disk flux from high resolution ALMA data to the envelope flux from lower resolution ACA data. And we can find sources that are envelope dominated, where most of the mass is the envelope, versus those that are disk dominated. And this gives us a better way maybe of classifying sources instead of using their SEDs. And it's sort of interesting, we're still digesting this, that all 5 of the erupting protostars have ratios less than 0.5. They all seem to be envelope dominated, and we do not find any that are disk dominated. And this is consistent with the idea that the outbursts are driven by the infall of material onto the disks, the material piling up onto the disks before they become unstable, presumably due to gravitational instabilities, and then that material is dumped down onto the protostars. Okay, and that might explain also why class 0 objects, which have the most massive envelopes, have the highest rates. And I'll end there. Thank you for your attention.
Okay, thanks, Dom. Thanks, Wafa. We have some time for questions. People can just unmute. I know I have one.
Yeah, I have a question. I think that was really, really fantastic work. Thank you so much for this presentation. I think it's really wonderful to see all the burst rate calculations, and I guess it's fundamentally with this level of statistics, assuming that all of the protostars are bursting at the same rate, right? But binarity or magnetic field strength or warped disks might affect this, right? So I wonder if you could talk a little bit about the timescales necessary or the sample size necessary to start to eke out some of these different mechanisms for bursting, how it might affect that calculation?
Maybe I'll address this. And wow, it's a good question. We actually did put that caveat in the paper because of a referee, very perceptive referee. And I haven't really thought through that because I think there's a lot of uncertainties there. As far as we know, none of these objects that I can remember are close binaries. So what might actually help is better measurements of which sources are binaries or what, and start maybe doing the comparisons, sort of categorized by better ways than just class 0, class 1, class 2. So all I can say is that this actually needs to be done, and as you sort of refine, as you sort of define more narrow classes like class 0 with binaries, class 0 without, yeah, then your numbers need to go up dramatically, and it's really hard to do this. So obviously, Steve, with the submillimeter work might be one of the better ways of building statistics, but I would think that you would want to be on the factor of like 10 roughly would be great. I don't know how you're going to get that in the short term. So
Yeah,
I guess it's sort of off the cuff. Maybe you've thought through this more than I have.
Probably
but,
not, but yeah.
Yeah,
Yeah.
it's a really good question, and we're sort of limited by the number of protostars, within 500 parsecs, right? And there's only about 600 of those, and so and about half of them are in Orion. So hopefully there'll be facilities that we can do to keep monitoring these in the mid-infrared or sub-millimeter in the future, so we can detect these bursts. But that's a real issue, actually.
Yeah, thanks for the insight.
Yeah.
So Wafa and Tom, that was a fantastic talk. Thank you. The question I have is trying to actually physically understand the timescales. I agree that I think that it's got to be that it's material onto the disk and then some instability in the disk. But if we're finding things on hundreds of years, I'm not yet convinced that I can make the disk go unstable that quickly. I sort of thought that the Chantenou and Edwards models sort of had longer timescales between the bursts because it took a lot of time to get the disk gravitationally unstable, or I need to move the material through the disk. So I agree with you. We're finding these shorter timescales, shorter than the more evolved systems, but I am still struggling physically with what that means. And I was wondering whether either of you have thought that a bit more.
I'm sorry, I'm trying to find my mute. Yeah, let me just respond to that very quickly. I think, I mean, there is the other factor is the infall rate, and I don't remember what Voiviev and Chantenou put in as their infall rates. I thought that their actual intervals between bursts could have been on the order of several hundred years, but maybe it was more on the order of 1,000 years. I thought a few hundred to 1,000 years was not a crazy number, and it's also sort of consistent with what people find by looking at knots and outbursts. So I didn't think that was much of a problem, but if your infall rates are approaching 10 to the minus fifth, maybe that's not a big deal.
I think what it's going to matter about are the infall rate and the size of the disk, right? So if you wanted the disk to be fully gravitationally unstable, the old number was, a reasonable fraction of the stellar mass, and that's hard to do, unless, and it's hard to imagine that you stopped it. I guess one possibility is the disk is just unstable, and the time scales involved in these bursts and between bursts are due to the instability in the disk, and it's not the picture of I remove the burst and now I have to pile more stuff onto the disk, and then I remove the burst and then I have to pile more stuff. It may be more interconnected, that the disk is unstable, it is trying to stabilize, and at the same time it's being continually added material to it.
Yeah, that's really interesting. So we did look at the properties of the disks as far as we could tell from the Van Dam survey, and I think some are resolved and some aren't. It's sort of an interesting mix. Like HOPS 124, HOPS 383 is close to being unstable. HOPS 124, I believe, is well. So it's sort of consistent with the disk being gravitationally unstable. HOPS 12 is not resolved, that particular disk. I have to go back and look at my notes. HOPS 124, by the way, has structure in it. It's got like a little like empty area in it. So yeah, there's a lot of, we need to think through this really carefully. But I guess the question is, how much, how fast we pile up material if its infall is 10 to the minus 5. It happens pretty quickly. And we have the disk masses. We can do this calculation.
And we
Probably
need
in
to
the next
connect to
hour
we
after
need
the
the
talk.
theorists, we need to be connecting between the shorter timescale events that some people have been playing with theoretically and the longer timescale events like the disk evolutionary events, but looking at them on the timescales of which we can observe now, because I think we haven't quite got the right theoretical models to play with. So we need to do the experiments. So if there are theorists listening, please talk to people like Tom.
Or Doug.
I think there are, but I'll call them. Can I ask you more questions?
Yeah, I'd like, this is Eric Becklin. I'd like to, very nice talk, Tom and Wafa. You mentioned, Tom, that future observations, but could you explain what you mean by future far infrared observations? Because the landscape looks
did I
pretty
mention that
bleak for
somewhere?
about 15 to 20 years.
Yeah, well, that's a good question. I don't know if I in what context I mentioned that. I mean, you know, in terms of future facilities, I think for doing the class 0 outburst, we're going to be very limited. You know, NEOWISE I don't know if it's going to go another year or so. There's, I think, some data from that. NEO Surveyor, this basically a planetary protection mission, actually will survey a large number of clouds, and so that might actually provide some more statistics. And then the submillimeter surveys may be the best way. But I guess, you know, in terms of the far infrared, it might depend, you know, if there's a probe that's developed in the next, you know, in 10 years or so, that could be another facility if it's.
It better be a pretty simple probe.
Well, you know, you could survey, you can do like a sample of 600 protostars every year. You know, it depends, you know, if it's like a Spitzer type agility, you could probably do that pretty effectively. We know where all the protostars are within 500 parsecs.
Yeah.
And so you could do that as a mission. I don't think that's actually as hard. But yeah, it's a little bit daunting to see how we go further and build up statistics. So with what we have available. And then once we detect burst, how to follow up on that.
Yeah. The other question I have is there are some regions of star formation that are closer, but do you see outbursts in those star formation regions that say are within 200 parsecs?
We have, yeah, you're talking about like
Forest enough samples to get any statistics.
Yeah, well, the problem is the numbers are smaller there, and the number of class 0 protostars is actually very small, within like 400, well, within 300 parsecs. You have to go out to Perseus. We're still sort of looking at some of that data now. There's actually a lot of unprocessed archival data on these regions that we haven't looked at carefully enough. But there have been some work with NEOWISE recently. I can't remember that may have found some of those bursts, but there's not many of them. I don't know if there's any other class 0 outbursts in Perseus that have been found. So I should know that. I think the NEOWISE database is probably the place to look at this point.
Time for one more quick question.
Comes along with that, which is once you start looking at these catalogs, it's not clear when something's a burst and when something's not a burst, in the sense that there's much more of a continuum along that axis as well. But Tom is absolutely correct that when you're looking for the rare events, Orion gives you a large enough sample.
Yeah, I think what would benefit us is to go further out, like do Cygnus X, for example. That would be, you know, the place to look, for example. But I don't see how we can do that in the near term.
I'd like to ask one more quick. How did you ascertain your confidence in the flux scale, especially comparing FORCAST and Spitzer data? I assume they're using different calibrators. And how did you really nail that down too?
Oh, well, we assumed everyone calibrated it, you know, correctly using so that we didn't worry so much about issues with calibration. You know, I mean, we're looking for factors of a few, not 10%. So I don't think that's a huge issue. I think the bigger issue was just the mismatch in the basically in the different wavelengths that you observe.
Yeah, and you explained how you factor that in. Yeah.
Oh,
you did. You had to.
Yeah, we did. We basically used the IRS spectrum, or we used a model basically to calculate what the color correction would be between the forecast bands and the MIPS bands. And so that's basically what it is. So you need to have an assumed model flux. This is always the case. When you want to go from an in-band flux to a flux density, you need a model flux. And when you compare those, or you need a model, a model spectrum to understand what the shape would be. And so that's what we did in this particular paper. And we found that the outburst amplitudes that we calculated were pretty consistent between the 25 and 31 micron band, but we're a little bit off for the 19.7. That may be that our assumption that the spectral shape from the IRS wasn't changing during the burst might have been incorrect. We're not exactly sure.
Okay.
So, yeah.
Thank you. Wafa, if you're here, I'd like to thank you for your presentation, and Tom too. This was really interesting and really in the scope of this series. So thank you for making that quite quickly.